Welcome everybody to one of the last videos in block 1 for TBMT 42. So we are now approaching the end. This is the second to last video, at least in the current version of the course. We will continue with nonlinear dynamics, so analysis of stability and now change of stability, which is something called a bifurcation. And we'll figure out how to draw bifurcation diagrams using something called continuation methods. So basically, we know how to do simulations, and now we want to do curves that look something like this, and we want to understand what is this curve. Okay, so let's understand the basis for a bifurcation diagram. So in the previous video, we understood that here, this looks like we have a fixed point. And here, the difference between the curves here is not the initial condition, because different initial conditions will typically end up in the same place if you have the same parameter. But if you have different values of the parameter, typically the fixed point will change, as most things in the model will change. So therefore, you can do a plot where you only plot the value of the fixed points on the y-axis, and on the x-axis you plot this parameter that you're changing, and this is called the bifurcation parameter. And this curve here that follows only the fixed points, this is called a continuation curve. So you obtain this using continuation methods. And the question now is, what happens if you move along this curve following just fixed points, fixed points, fixed points, and you meet another fixed point? Or if something happens to this fixed point, it might lose its stability, it might gain stability. What then? Well, then we have a bifurcation. So that is what the local bifurcation is about. So let's draw this type of curve. So here we have a stable fixed point moving along happily. And here it crashes into an unstable fixed point. So they collide and they annihilate each other. So after this, there is neither a stable nor an unstable fixed point for larger values of the bifurcation parameter. So this here, so here we have a stable node, and this is called a saddle. So therefore, this is called a saddle node bifurcation. Or another name for this very, very common local bifurcation is a blue sky bifurcation. And why is that? Well, it's because if you move here from the right, you have no stable behavior at all in this area, maybe not at all, maybe the whole model is just diverging here. And then suddenly, out of nothing, no warning whatsoever, suddenly out of the blue sky, you have a stable fixed point. So the model is actually turning towards some kind of reasonable behavior in this area. Or from the other point of view, you're sort of moving happily along, and suddenly you lost all your stability. So that's why it's called the blue sky bifurcation. So that's one of the most common ones. Another common one is if we have a stable fixed point that we are continuing up as before here. And then it will become unstable. So it turns into this red one. But at the same time, there is stable oscillations that appear around this. So if you start here at the fixed point, you will stay there. But if you start a little bit away, you will diverge because it's an unstable fixed point, the red one. But you won't diverge forever, as you will do over here. Here you go to some completely different place, maybe infinity. Here, you will only go a little bit above. So you will go to an oscillatory behavior here. And this is now, as we learned in the previous video, not a fixed point, but it's a stationary behavior. So it's a long-term behavior that goes on forever, and it's a limit cycle. So here we see, as we move along in the bifurcation diagram, the amplitude of the oscillations increase and they get bigger and bigger. And this is the typical behavior of a supercritical Hopf bifurcation. So that has that behavior that we have here, a stable fixed point that becomes unstable, and the stable fixed point is replaced by stable oscillations. So from a distance, if you look far away, and you don't really zoom in here, but you just see, oh, this looks stable. It's sort of oscillating, but it goes to a fixed point. And here it looks like it's going to a fixed point still, because the amplitude is very, very small in the beginning. So you can't really see that anything has happened from a distance. That's a supercritical Hopf bifurcation. There is also a subcritical Hopf bifurcation, and then you jump immediately to much larger oscillations. It's a different type of bifurcation. So if we look in a three-dimensional plot here, and this is the one from the first page, then we have the bifurcation parameter here on the x-axis, and here we have x1, and here we have x2. So before the Hopf bifurcation, which we have here, then we will have something that sort of looks like a limit cycle, but the limit cycle collapses down to a point. And here at the bifurcation, this is where we have that one of the eigenvalues to one of the eigenvectors, or actually two of them, because this is a two-dimensional bifurcation, will have zero real part. So here we have a center space, and it's on this center space that we start to have these oscillations. These limit cycles start to grow on this center space. Then eventually start to leave the center space and go out of the center manifold. And this is the stable limit cycle. So it will sort of turn around here. And as you move away here, the limit cycle, the amplitude of limit cycle will get bigger and bigger. So this is what the supercritical Hopf bifurcation looks like. So then you might ask, how complicated is it to get this type of behavior? Well, you can actually get them with very simple models. So this very, very simple model is just dxdt equals r, which is a parameter, plus x squared. This is the bifurcation parameter, and this will yield a sudden node bifurcation. So this is actually the normal form. So it's the simplest way that you can get the sudden node bifurcation. And it's a normal form means that you can transform any model, no matter how big it is, to this normal form. And basically what you're doing is that you're projecting the multidimensional dynamics. Maybe here you have a very big model down to the center manifold, which is on the center space, this spanned by the eigenvectors, which has a zero real part. And on that one, you can even do a nonlinear transformation to get to this particular form. So this is, we won't go through the details of how to do this, but I want you to have at least heard these type of concepts. So let's just give an example of showing that these type of things actually appear in nature. So here is a Hopf bifurcation from synchronizing metabolism in a baker's yeast cell. So Saccharomyces cerevisiae. And here we see oscillations. Here we're looking at NADH. And here we do a perturbation. So we move away from the limit cycle for a while because we are perturbed. But then very rapidly we come back again. And in fact, here we see the simulation of a normal form with the model. So this model was published in 1999 by Sune Dale. And then they published, or this experimental condition was published in 1999. And then in 2001, they published a detailed model for this system. So here we have glycolysis. This is an ordinary differential equation model with 30 states and 50 parameters. But this gigantic model can be mapped to a two-dimensional system. So this is, it looks like it's one-dimensional, but this is actually a complex number. And we have 4 parameters here. So this is the frequency, and this is the amplitude, and so on. So these are the parameters. And all of the many 50 parameters here, they can be mapped down to these 4 parameters in the normal form of the Hopf bifurcation. So this is normal form theory is very powerful. And this means that this 30-dimensional dynamics can actually be described on a 2-dimensional manifold. So no matter how big the original model is, the bifurcation and the limit cycle is always a 2-dimensional phenomenon, at least close to the bifurcation. So finally, something about continuation methods. How do we actually generate these curves? So we want to have this fixed point following here. And the basic idea, we won't go through the detailed math of how to do it. It's not that difficult, but we draw the line somewhere. We draw the line here now, at least in this version of the course. So here we have the bifurcation parameter. Here we have a fixed point. And then you can look again at this Jacobian and certain directions to figure out what is a reasonable direction to go in. So this gives you the predictor step. And then you know that it's a fixed point. So you know that f of x at this new place for this new parameter should be 0. So you want what is the fixed point, what is the state that is a fixed point for this new value of the parameter. And this you can solve using some Newton-Raphson or some local solver. And this is called the corrector step. So what you should know is that continuation methods are typically constructed in a predictor corrector step fashion. So we won't go through the details of how to construct this, but it is using a predictor corrector step approach that you get this continuation methods. And if you want to figure out where the bifurcations happen, so here we have this Hopf bifurcation again, then you also need to keep track of the eigenvalues to notice that. And in fact, you can even do, once you found this bifurcation, you can even follow the bifurcation in a 2-dimensional plane where you have no space at all. So here you have one parameter, and here you have another parameter. And then you have all of these are Hopf bifurcations. So here we have steady state behavior, and here we have oscillations. So all of these are Hopf bifurcations in the parameter space. So this is also the result of a continuation. Okay, so now we learned what a continuation method is and what 2 of the most common bifurcations are, saddle node bifurcation and a Hopf bifurcation. Okay, that was it for this video.